Hello, scholars. Welcome. Professor Hinkle here. In today's lecture, we are going to discuss coastal oceanography. The coastline is the interface between the ocean and land, and it behaves in systematic and understandable ways. It is very dynamic, producing different types of features that are associated with the relative processes, quantities of sediment that are available. So lots to talk about as far as oceans go. Here we go. When most people think about coastlines, they think about the beach. Let's go to the beach. We're talking about let's go to the coastline. And when we talk about going to the beach, we talk about let's go lay on the sand. What is that sand? Usually when we're thinking about it, it's white sand beaches composed of very resistant quartz mineral grains that have traveled long distances and become very rounded. Sand on the beach. But coastlines are more complex and they're not exclusive to that type of beach. So we have beaches along the coastline. They're made of the material that is locally available. The rivers are delivering sediment from the mountains. We have the coast, the bluffs that are eroding material directly to it, and then any biological components that might be nearby that could deliver their material to be beach sediments. These are extremely dynamic, highly mobile areas that transfer the sand down the coastline in ways that we are going to discuss here. So we get a variety of different types of beaches, from black sand beaches on volcanoes to beaches composed entirely of shells near coral reefs, to rocky beaches with bouldery material, to our quintessential idyllic white sand beaches, palm trees, very tropical, gorgeous, clear water. Beaches come in many shapes and sizes and types. There isn't just one type. And some places lack sand altogether. Rocky coastlines host a variety of different types of benthic organisms that don't like the sand, So there we go. Okay, let's look at a shoreline. Offshore. It's where waves begin to develop. A longshore bar can deposit. We've got a trough underneath. Breakers actually break in the surf zone. This is all part of the near shore environment. When the waves start to break, they're in the foreshore, and then above waves breaking is the back shore. The swash zone is where you have the beach face, and where we like to go hang out and put our chairs and our towels and our umbrellas in the sand is actually the berm. It's not even the beach face. This is, what we consider the beach is all of it. Interchangeably, we call the coastline the beach. The beach face is actually the area between high tide and low tide, the intertidal zone. The berm, this is where we like to hang out and enjoy the sand between our toes and soak up the rays and the sunshine. So here's all your definitions. This is a good place to study for understanding these various zones that I just identified. Beaches are dynamic through time and space. So in the winter there's big storms and big waves are crashing along the shore. In the summer, mellow, not big storms. That's why we like beaches in the summer. Also because in the summer those mellow waves bring sand from the longshore bar onto the berm. And in the winter, that sand is ripped off the berm and taken out to the longshore bar. Changes the geometry of the beach face, making summertime beaches the time and place to go hang out, to dip your toes into the sand. Movement of sand along the beach. So we have this concept of subtropical gyres. Clockwise in the northern hemisphere, counterclockwise in the southern hemisphere. And if we draw a picture of California, Our subtropical gyre is in this direction. That means that surface currents along the coast of California are from north to south. This is the direction of longshore currents as dictated by atmospheric and oceanic interactions, because the Earth spins on an axis. Once a day, the Coriolis effect, creating subtropical gyres, preferred directions of surface currents, giving us the movement of water along a shore known as the longshore current. Now, the movement of sand in the direction of longshore current is longshore drift. And the sand moves like this. The direction of longshore current is from left to right. So, this way. Shown. As waves approach, they refract or bend so that the incoming waves are nearly parallel. It moves it, sand or sediments, at a slight angle up, waves coming up the shore, swash, and washing back down the shore, backwash. Up the shore, swash, back down, backwash. The swash moves sediment or sands in the direction of longshore current. Backwash, gravity brings it straight down. Over and over and over again as time goes on, the longshore drift of sand is in the direction of longshore current. Let's check out this video on longshore drift. It really summarizes it. Longshore current and longshore drift is also why when you're hanging out, you got all your stuff, and you're like, I'm going to go swimming right now, and you're in the water, and you're like diving under waves, and you're jumping over waves, and you're having a great time, and then you get out of the water, and you think, wait, where'd my stuff go? Oh, it's way up there. What happened? Well, your stuff didn't move. You moved in the direction of the longshore current. Sand does the same thing. It moves in the direction of longshore current. So check this out. I think you'll like it. Something to be cautious and cognizant about are rip currents. So rip currents are very hazardous. They kill about 100 people every year. Maybe thousands more, but about 100 reported cases. And this happens when breakers crash onto the shore. There's a gap in the longshore bar and a swift water that will pull all the way outside of the surf zone. Now, if a person gets caught in here, the reason that people die in rip currents is as such. Swimming along and then all of a sudden, whoa, getting pulled out to shore. And so the reaction is swim as hard as you can. Swim, 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 swim. Well, people who try and swim against a riptide get tired. They sink to the bottom and they drown. Two things you can do. Nothing is one. Let the riptide take you out. It'll push you back around into the breakers, which will then you can swim very easily back to shore. Or you could swim sideways. But which way do you swim, left or right? Well, you want to go in the direction of the longshore current, because if you swim against longshore current, then it might just push you right back in. You get tired and you'll die. If you swim against or in the direction, you'll swim right out of it and then get pushed right back to shore. So the number one thing, if you ever find yourself in a rip current, don't panic. Take a breath, relax, swim, either do nothing or swim in the direction of the longshore current. You'll be able to safely exit the rip current and you will be okay. Perfect. So let's talk about different features that we'll find along coastlines. And the features are going to be dictated by the dominant force. Is it erosion or deposition? Now, in all coastlines, there's erosion and deposition happening, but certain coasts favor one or the other, and we'll call them erosional shores, where we have well-developed cliffs that exist where tectonic uplift of the coast occurs, or depositional shores, more on that to come. Erosional shores focus wave energy on headlands and dissipate wave energy in bays. Now, this creates a variety of features we see here as sea stacks and sea arches, ultimately leading to coastal straightening. more of these defined right now. In erosional shores, you can see there's no sand here. This is a wintertime beach. There might be sand here in the summertime. The sand is deposited in the longshore bar. It's also at low tide. Wave action carves this area very flat. It erodes into the substrate, creating what is known as a wave-cut platform or a wave-cut bench. If this bench is uplifted or sea level drops and cuts a new one, it forms a marine terrace. Now, this is a headland that extends out into the water. High tide, low tide, you can see the difference. Tide is the daily rising and lowering of ocean sea level at coastlines. The sea arch connects a chunk with the piece eroded out underneath. When that erosion continues, it leaves a sea stack. Sea stacks are very exemplary of the Pacific coast. There's certain instances where underneath you can see a sea cable form and then a little conduit up to the surface where air and shooting water will be pressed through when water comes into the cave, forms a blowhole. They're really cool features. If you're ever on a coastline and you get to see one, they make a lot of noise. You hear the waves coming in, and then you hear, and you see a bunch of water being shot up out of this hole in the top of the rock. Super cool. Okay. Evolution of coastal straightening on an erosional coastline to create all the features we saw. So, an irregularly shaped coastline following tectonic activity. Wave energy focused because of refraction on headlands. Erosion happens, cutting back, giving us sea arches, sea stacks, and sea caves. Over time, the coastline becomes nice and straight. Certain areas favor deposition. These are tectonically inactive areas, giving us deltas, sandspits, tombolos, baymouth barriers, barrier islands, and creating lagoons. Lagoons can be created anywhere. Well, I'll get into that. But these are depositional shores where the shores are subsiding. We get lots of sand deposits. Sandy deposits are the most common. Here we can see the coastline, and then extending out of the coast is a large swath of sand known as a sand spit. We get coastal deposition where rivers that transport a lot of sediment meet the ocean also. When that river transporting all that sand can no longer transport because of the intersection of the ocean, it deposits those sediments. These sediments disperse, and then the river needs to carve through them into what are called distributaries, that are branching channels of sediment being carried to the ocean. This is a very cool depositional shoreline feature of which we can see in this informational video. Please watch now. Welcome back. Okay, so some features. When sand extends into the ocean, as mentioned, it forms a sand spit. When that sand spit goes all the way across a bay, that sand spit will become a baymouth bar, as we see here, and it forms a coastal lagoon. Our last feature here that we can see in this image is a tombolo connecting an island to the mainland or a leftover sea stack to the mainland. Tombolos are pretty cool. Here we see an island, rocky shore, low tide, sand that connects the two of them. Longshore currents, moving sand, longshore drift in this direction, starts to accumulate on either side. As that sand accumulation grows, it connects, giving us a connected mainland to the island, thus a tombolo. Barrier islands are parallel to coastlines. On depositional shores, you don't really get these on erosional shorelines, and therefore you don't really see barrier islands on the Pacific coast. You see sea stacks, sea arches. But on the East Coast, It's almost completely lined. The Gulf of Mexico, the Atlantic coast have 300 of the relatively 2,000 global barrier islands. The United States has the most barrier islands, and barrier islands are active, dynamic features, and in certain areas like Miami Beach, highly developed and populated, which we'll get into more aspects of that here to come. This is a great time lapse over about 15 years of barrier island migration and development. Check this out now, please. So our discussion to this point is coastlines are dynamic and sand moves along coastlines. But what if when you or I or people don't want that sand to move? Because we value sand on our beach. But sometimes natural processes say, we're going to move the sand off the beach. We're being the natural ecosystem, the coastline itself. Well, humans come in and they build structures known as hard stabilization to decrease coastal erosion and interfere with the movement of sand. And we've got jetties, groins, and breakwaters. Let's talk about them. A groin is a wood or concrete structure that traps sand. Here you see more sand on the right than on the left. Longshore drift is from right to left, trapping the sand behind it. In this one, we've got a groin, a groin, a groin, a groin. This is a groin field, halting the movement of sand, where sand builds up on one side, not on the other, so on and so forth. A jetty is two groins that are perpendicular to each other that connect the ocean to a harbor. Here you can see the harbor with a bunch of boats. Lots of sand. Longshore drift is from left to right here. Sand builds up. Often you'll get a sand spit that will form that has to be dredged out and removed. Because the value here is to protect the harbor and keep it connected to the ocean, harbors protect boats from big storms. So keep the boats from getting damaged in the big storm, keep the boats going out to the ocean by building the jetties. Another option, breakwaters. So here we can see the sea is a little bit more turbulent than it is over here where the boats are, because incoming wave action is blocked by the man-made structure, the human-made structure of the breakwater. Now, these all are good in theory, but what happens when we start to disrupt the natural movement of sand? Unexpected consequences. Yes, like we see here. I have a great idea. Okay, so let's build a breakwater. This happened in the 30s and 40s on the Santa Monica Pier, right here. We wanted to protect the Santa Monica Pier so people could enjoy it all year long, enjoy the sand on the beach. Here's the breakwater, and then a humongous bulge of sand started to develop. The sand started to encroach on the pier, and then this breakwater was removed because of the unexpected consequences, the unforeseen, because sand is going to keep moving. It's a natural process, and sand responds to the geometry, to the profile of the coastline. When you add in these various things that disrupt that, it is going to respond in one way or another. One last option, when coastal erosion is occurring and the sea cliff is eroding back, sometimes it can undermine homes that are built on the right beachfront property. Building a concrete barrier. So we can see here it's broken, sand is peeking through. These will ultimately break down. This material will become part of the beach sediments. They'll need to be repaired or replaced. So not a long-term solution, but these types of solutions can slow down or not halt, but really decrease the speed at which beach erosion is occurring. So if these human-made structures provide temporary solutions, they're very disruptive, what can we do? What should we do? Well, that's a big question, but what could we do? Well, we could restrict the construction. Here you can see large blocks of riprap that are blocking incoming. This is essentially trying to form a seawall, but coastal erosion is still occurring. You can move the structure back 100 feet. You could not let anybody build there. People don't like this, though, because don't tell me what to do, and definitely do not tell me to move. This is my house. I was here first. Or you can put sand back on the beach in this beach nourishment or beach replenishment. So this is a great Vox investigative journalism special on beach nourishment. You will learn a lot. Check this out. Couple more aspects of coastlines. So lagoons are going to be locations where spits, barrier islands, or some other feature partially cuts off a body of water from the ocean. First, we have to have the right type of coastal geometry to happen, and then it cuts off. Estuaries are going to be very similar to lagoons, but we're going to have an input of fresh water from rivers that creates brackish, a mixture of salt and fresh water. So we've got 4 specific types of estuaries. Excuse me. Coastal plain. This is where sea level drops and rivers cut down, forming big valleys, and then sea level rises and it floods those valleys. Very similar to Chesapeake Bay, which we see here. This is a coastal plain estuary. Another one up here. East Coast, got it. Fjords. During periods of glacial extent, glaciers carve down river valleys, forming these big U's that then the glacier melts, leaving very steep-sided estuaries, mixtures of the river. Here comes the incoming river with the ocean. Incoming river with the ocean. This is a key feature of estuaries. Barrier islands create their own type of estuary where they can ring these lines all the way around, again, popular on the East Coast, right? Depositing sandbars that are parallel. We see these on the U.S. coast, East Coast, and Gulf Coast. And last but not least, tectonic. This is the type that made the San Francisco Bay estuary. West coast of North America, highly tectonically active. Right now, California's margin is a strike-slip fault, so large continental transform boundary, but it wasn't always. And at one point, there was faults that downdropped relative to the surrounding mountains, giving us this mixture of salt and fresh water. Now, this is important to know, right? Because there's a mixture of salt and fresh water. So how do they mix together? Well, they could completely mix, right? Shallow, low volume, net flow from the head to the mouth where it's completely vertically mixed. Or you can have a stratification where fresh water will be on top, salt water will be on low, slightly stratified or highly stratified, or the fresh water can push in and not mix, forming a saltwater wedge, which is essentially this upside down triangle. So let's take it to some of the effects of human activities. We talked about in another lecture the process of eutrophication, which is human impacts of land, the runoff of nutrients and fertilizers that's delivered to the ocean, causing a boom of primary productivity, specifically algae, which dies, falls to the bottom, and then the decomposers decompose that extra marine life, removing the dissolved oxygen from that system. Chesapeake Bay, slightly stratified, with large seasonal changes in salinity, temperature, and dissolved oxygen. And the maximum freshwater river flow is in spring, meaning that spring would be a good time for dissolved oxygen. But what we see here is areas become extremely depleted of oxygen in what are called anoxic, without oxygen. If we look at a profile, 1950, Beautiful mixing. We go to 1980. The bottom is completely anoxic. Marine life needs oxygen to survive. Without oxygen, we have dead zones. That's the word. Awful. Dead zones. And so from May to August, when river water starts to slow down, we get anoxic conditions that are killing marine life. In the case of the Chesapeake Bay, specifically, the oyster populations are decimated in decline. Our final discussion for coastlines is going to be the natural filters of these coastal systems in the form of wetlands. That includes swamps, mudflats, coastal marshes, bayous, salt flats, and mangrove forests. So here we can see Morro Bay. The tide is out. There's Morro Rock, exposed muddy areas with a wetland marsh just inland of that. This is where fresh water, coastal water, the water table is usually pretty close. So you get a high amount of freshwater input to support freshwater species. Salt marshes, so cool. Small brackish ponds, these support salt-tolerant species located between 30 and 65 degrees latitude. The influence that latitude has on biodiversity and climate and atmospheric circulation is amazing. 30 to 65, these are the Ferrel cells. So very specific bands of atmospheric convection patterns in or on Earth. Mangroves are coastal forests. Here we can see the overstory full of trees, the understory, the roots grow down. This is a low tide, so you can see the roots growing directly into the dirt. High tide will come up to about the base of the level of these trees. They're really important places of biodiversity, very diverse ecosystems that create habitat, security, protection of coastal areas, which takes us into some of the benefits. Diverse plants and animals, highly productive ecosystems. Nurseries for more than half of commercially important fish. They soak up nutrients. They're filters for heterogeneous pollutants, removing inorganic nitrogen, metals from the environment. They're protective barriers to erosion for coastlines that dissipate coastal wave energy and absorb excess water. So, wow, wetlands are so important. We must take such good care of them, right? The value of wetlands must be tremendous. Well, getting there, but it hasn't always been that way. Over half of the wetlands in the United States are gone because for a long time it went like this. Look at this beautiful land, but it's covered with all this water. This awesome oceanfront property. I know what to do. Fill it in with sediment. Move this pesky river so it doesn't even drain here. Now let's build on this land. Well, now we know. We probably knew back then, but now we for sure know because of our understanding of oceanography, our understanding of coastlines, that for all the reasons aforementioned, coastlines are important. So wetland restoration is a huge, huge business right now. You can dedicate your life to restoring wetlands, and it would be noble work because coastlines are dynamic interfaces between the ocean and land. There's a lot of movement of material between ocean and land. Ocean sediments develop on land, and for these sediments to filter through coastlines is absolutely important. So I mentioned that, but in conclusion, coastlines are that interface, land and sea. They can be erosional or depositional depending on the local geology. There's a lot of features that develop from the processes, specifically erosion or deposition, and these coastlines are important for a broad array of habitats, for protection, for biodiversity in general. So that's our lecture on coastlines. I hope you enjoyed it. I hope you learned a lot. Thank you for your attention.